Okay, good morning, everyone. Normally Alicia Weinberger would be here this morning to introduce Jackie, but she's trying to sleep, I'm sure, right now. She's remote observing last night using the Planck telescope in Chile, so she asked me to take over as a pinch hitter. So I have the honor of introducing Jackie Faherty this morning. Jackie did her undergraduate work getting a BS in physics at the University of Notre Dame in 2001. Then she went to the State University of New York in Stony Brook. Got first a master's in physics again, and then a Ph.D. in physics and astronomy in 2010, working with Fred Walter, Adam Burgasser, and Michael Shara. Michael Shara is an astronomer at the American Museum of Natural History in New York, and so it's quite natural for Jackie to go to take a postdoc at the American Museum of Natural History for a year. And while she was there, she competed and got an NSF International Fellowship. And so she had a chance to go anywhere in the world she wanted to, and for some odd reason decided to go to Chile, University of Chile in Santiago, because after all, Chile is essentially the center of the astronomical universe these days for both optical and millimeter wave astronomy. So she spent a couple of years in Santiago, and while there, competed to get a Hubble Fellowship, which is again another highly competitive, prestigious fellowship, and she won that as well in 2013. And the great thing is she decided to take that Hubble Fellowship here to us at DTM, for which we'll be eternally grateful. It's wonderful to have another Hubble Fellow here. So we're going to be hearing today about our Brown Dwarf work, and the important part of her title is that yesterday happened to be the 450th anniversary of the birth of William Shakespeare. So it's a quite appropriate title, and that was of course a part of Hamlet's soliloquy, so he was talking to himself, but we will pretend that Jackie is talking to us today about Brown Dwarf. So Jackie, take it away.
Thanks, Alan. There's no Shakespeare in this talk, unfortunately. So as Alan said, I just joined DTM here, and I came here sight unseen. Alicia gave me a Skype tour of DTM, which was enough for me to say, this place looks amazing, I'll take the Hubble there. I had originally been scheduled to give a talk here in the astronomy department by Guia Mangalata, who was a postdoc here and organizing the seminars. And I don't know, we had our communication cross or something. He emailed me the day before the talk and said, Jackie, what time is your train coming in? And I was like, I'm defending tomorrow. I don't know what you're talking about. So we didn't reschedule that. It's funny. Okay, so today's talk is on the work that I've been doing. The title was To Be or Not to Be a Planet. The To Be or Not to Be part, you guys can have your own opinions. At the end of this, every scientist working in this field has an opinion whether the objects I'm going to tell you about today should be considered planets, should be considered brown dwarfs. I'll tell you what a brown dwarf is because I'm sure some people in the room are thinking, what the heck is brown things? But this field right now is, in one word, amazing. We are breaking ground in a way that is so exciting. It is the discovery of objects that are exotic. It is the discovery of objects that just invoke amazing, creative, imaginative exercises in what kind of life might be out there, what kind of life might exist in the universe. So I'll lead by introducing why you should care about these objects that I'm going to tell you about, brown dwarfs. And that is that we are currently living in the era of exoplanet characterization. We're out of the era of exoplanet detection. Paul Butler is one of the pioneers in enabling us to detect exoplanets. But now, we're not just detecting exoplanets, we're actually characterizing them. We're getting light directly from the planet, and we're able to take the light directly from the planet and say something about their atmospheres, say something about their chemistry, say something about how they formed. This is an amazing time. It's in part because of these missions. So the Gemini Planet Imager, which is an adaptive optics coronagraph and spectrograph that's on the Gemini telescope in Chile right now. Sphere is a competitive, similar instrument that's on one of the large telescopes, the very large telescopes, imaginative name for a telescope, in Chile. Project 1640, which is on the Palomar telescope, JWST, which is upcoming. All of these missions have one, well, JWST has multiple goals, but they have a main mission, which is to turn the the telescope to a planet and figure out what it's made of, so we can say something about what's out there. And so what I'll argue today, that the key to understanding the data that we're going to get flooded with GPI, with SPHERE, with Project 1640, and with JWST, are the brown dwarfs. The brown dwarfs are the key. So what are the brown dwarfs? This is the picture of stuff that can form, technical term there. You've got stars. This is an image of our sun. This is actually an image of our sun from 2 days ago in the ultraviolet taken by the SOHO telescope, which is orbiting, it's off in space. This is an image of Jupiter. And so in the 1960s, there were theorists that were sitting around, as theorists do, wondering what is between stars and planets, or what's the lowest mass thing that you can form via the same processes by which you form, say, stars. And the answer came in the form of these objects we now call brown dwarfs. Brown dwarfs are in mass space directly between the lowest mass stars and the highest mass planets. And you'll see in a few slides that there's also tremendous overlap between the lowest mass brown dwarfs and the highest mass planets. The brown dwarfs are essentially objects that are forming like stars, collapsing from a giant molecular cloud, but as they're collapsing, they're contracting, their radius is getting smaller and smaller and smaller, their cores are getting hotter and hotter and hotter, hot enough so that you can reach a temperature by which you can get nuclear fusion, the definition of how a main sequence star burns. But in the case of the brown dwarf, something happens, and that something is called electron degeneracy pressure. At some point, the electrons get squashed together too much and push back. And when they push back, everything stops. You can't get a higher temperature. And so the object just ends up cooling. So you can't get a core temperature hot enough for nuclear fusion. That's the definition of the brown dwarf. They were theorized in the 60s. It took 30 years of searching to find them. And that's because brown dwarfs give off the majority of their light in the near infrared. So this is a plot of the basically flux versus wavelength, applying Wien's law, which shows you what the emergent flux looks like coming from a perfect black body. So brown dwarfs aren't perfect black bodies, but this is a good estimate. You can see that at, say, 1,000 degrees Kelvin, brown dwarfs are basically objects that are below 3,000 degrees Kelvin. Our sun is here at 5,700 degrees Kelvin or so. You can see that these objects, as you get to lower and lower temperature, less light is in the visible. So this isn't projecting quite nicely, but this is highlighting for you where the visible light is, which you see with your eye, the optic, or what we call the optical light. For these objects that are in the brown dwarf temperature regime, their flux is coming in the near infrared or the mid infrared. So you have to go to the infrared wavelengths in order to study these objects. You have to go to the infrared wavelengths to study your exoplanets as well. Mid infrared is also extremely important.
Is 0.12 solar masses a good lower limit, or is it fuzzy?
The lower limit is actually, it's metallicity dependent, but it's largely set at 75 Jupiter masses, or 0.075 solar masses. It's about, so a thousandth of the mass. Or sorry, Jupiter, we usually talk in Jupiter masses. Yeah, so they're smaller, sorry. The 75 Jupiter masses is the mass limit for brown dwarfs. We usually talk in Jupiter masses for brown dwarfs because they're more similar to Jupiter than they are to the sun. This is what the spectral energy distributions look like for a series of objects. At the effective temperatures of the brown dwarfs, 3,000 degrees Kelvin or lower, you get crazy atmospheric chemistry. Their spectral energy distributions are regulated by gas and condensation chemistry. So at the higher temperatures, you've got things like metal hydrides, you've got iron hydrides in their spectra, you've got potassium lines, you've got titanium oxide. Then as you get to cooler temperatures, and actually what will be a main part of my talk is this atmospheric chemistry, because at these temperatures you get crazy mineral species clouds that are in these objects. As you drop down to lower temperatures, methane becomes an important absorber, and so the objects have a lot of methane gas in their photospheres. When you get down to the temperatures of Jupiter, so you have some methane, but ammonia is important. So spectra are extremely important to obtain, extremely difficult to obtain for exoplanets right now, but I've got a whole bucket load of spectra on the brown dwarfs that we can use to really ground our understanding of future exoplanets. But to give you a couple glossary terms of what I'll say over and over again in this talk, I'll talk about their colors a lot. So the color term, rather than talk about the spectral features, which can get a bit jargony and technical, I'm going to talk more about their colors. So you can look at the broadband filter, take a broadband filter, and then look at an object. Doing photometry, take the difference in the J band and the K band flux, or rather the 1 micron and the 2.5 micron flux, or what I call the near infrared color. Also refer to this as the J minus K color. This is an important diagnostic tool for looking at the features of these objects. We also have the mid-infrared colors. At 3.5 microns and 4.5 microns, you get a lot of flux, important areas of the spectral energy distributions. And I want to highlight the two most important missions in brown dwarf science thus far. Other people might argue with me, but whatever, they're not in the room. 2 micron all-sky survey, which was running from 1998 to 2002 or 3. This cracked the game wide open because it was the first all-sky survey in the near-infrared. Many, many brown dwarf discoveries came out of that. And then there's WISE, the Wide Field Infrared Survey Explorer, that's still currently in operation, that recently released their all-sky survey in between 2010 and 2012, and this has really done an amazing thing for cold brown dwarf science, and the objects did slam against the Exoplanet Mass Boundary. So I will be referring to WISE colors and near and mid-infrared colors from WISE. WISE, 3.5 and 4.5 microns, they label their filters with W1 and W2. That just means it's mid-infrared color, if I slip into too much jargon, and then near-infrared color as well. All right, one more introductory slide, and this is the most important one of all the introductory slides.
JK colors are the standard Johnson system.
That's actually in 2 mass filters.
2 mass filters?
Yeah, so 2
They're
mass filters are different than Johnson. And that's actually a K short. It's not the typical K, but it's 2 mass filter bands.
Okay.
So this is the single most important plot to understand for why brown dwarfs and exoplanets are so important to study in harmony with one another. That's because you've got a very clear problem here if you want to study an isolated object. So first let's go over the axes. This is the age of an object from about 1 million years to 10 billion years. We're sitting on a 4.5 billion year old star or thereabouts. So we're somewhere at mature age. We don't like to call things old. The temperature is on the y-axis here, and now I'm talking about cold things, essentially, from 500 degrees Kelvin to 3,500 degrees Kelvin. Every one of these lines shows you what something of the same mass would be doing. Now, what we find out there is isolated objects. And so if you didn't know the age of the object, you actually wouldn't know what you're studying. So if you found yourself your favorite, say, L5 type object, this is measuring effective temperature is quite difficult for many reasons, so we use the spectral characteristics of it, or the spectral type is our probe for effective temperature. And what you'd see if you pointed a telescope at an object, found your favorite object, and it looked like it had effective temperature through its spectral type of about 1700 degrees Kelvin or so. If that object was very, very young, in a star-forming region or a star-forming region that's evolving, that's a planet. If that object is a bit more juvenile age, 100 million years, maybe in the Pleiades, maybe the Hyades even, that's a brown dwarf. If that object is sweeping in from a halo, or even just your generically evolved thin disk star, a star that's in the Milky Way disk, it's a low mass star. All 3 of these objects look exactly the same. They have the same effective temperature. So there's overlap. So it's perfect, because planets are really hard to study because you have to block out the light from a star in order to get to them. Brown dwarfs, on the other hand, are isolated. And you can just study those and throw the whole problem out the window in terms of getting your spectral information from the planet, and let's just use the brown dwarfs to really nail down what's going on, which is what we've been doing. So I'm going to approach this problem in the talk has two main focuses. The first focus is going to be on the young brown dwarfs, objects that range between 1,000 degrees and 3,000 degrees Kelvin, or 10 and 100 million years. So this area, and you can see this area has overlap between planets and brown dwarfs. And then the last part of the talk is going to be on, yeah.
Just to clarify before you go on, so you're basically distinguishing which category by context, given that one temperature could be one of several different types.
Yeah, so I forgot to mention that the difference between a star and a brown dwarf is that stars have nuclear burning. Brown dwarfs, this kink at the beginning here means that there's some heavy hydrogen or deuterium burning. So the brown dwarf has that. Now, at the planetary mass, there's no kink at all. And so the actual color coding has more to do with the effective temperature and what kind of burning you can get going on in them.
But if you measure something's temperature, effective temperature, how do you know? You just said it's non-unique.
Yeah.
So how do you decide whether that thing is a planet? I mean, if you don't know its age, or
Yeah.
do you get that out of context of where?
Right, so then you don't know. So that there's certain things that you can know because objects that are this young, when they're as young as 1 to 10 million years old, the fact that they are a lower surface gravity will drive some important changes in their spectra. But they look a lot like an object that's a brown dwarf. So you actually don't know. I mean, you really can't tell. It's unlikely that you've got, of the thousands of brown dwarfs that we're studying, that they're all planets because they're all young. That doesn't make any sense. They're not associated with anything young. You wouldn't just have free-floating objects out there. But this might become clearer as I go into these objects, because this is where things are a little bit confusing, because the primary thing that tells you what kind of what the temperature is for the object, hence what kind of object it is their spectral energy distribution, the characteristics in their spectra. And we can pull out things from that spectra that give us some age indications that would tell us one way or another what they are. Okay, so the two focuses, focus number 1 will be on these young objects, and focus number 2 is going to be just on cold brown dwarfs. And I'll say that focus number 1 has been my primary scientific agenda as of late, though focus number 2 is amazing, and even if you fall asleep from the beginning, you should wake back up for this part, because I'm going to tell you about an object that's so off the charts amazing that I think it should blow everybody's mind in the room. Just wake up again in 30 minutes. Okay, so focus number 1, though, is on the young brown dwarfs. Why do we care about the young brown dwarfs? This is the reason. This is a gallery of images of directly imaged exoplanets. And this is the age of the objects versus the effective temperature, essentially the exact same plot. I've just zoomed in on it. The handful of planets that we actually have information on, we can take a telescope, turn and point to it, and get directly imaged data on it. All of the directly imaged exoplanets to date have an effective temperature squarely in the brown dwarf regime. So finding those in isolation, you would find yourself confused as to what the object might be. We know that they're orbiting a star. In this case, actually, 2MASS-1207b is orbiting a brown dwarf. But these other objects, they're orbiting a star with a well-known age. And so we know that they're orbiting that star. You assume that they're co-evolving with it. You have an age. You're able to say something about the mass. These objects all tap in to below or thereabouts below 13 Jupiter masses, which is the classic boundary where you can get deuterium burning or not. So here's the directly imaged exoplanets. I'll come back to these objects again. This is like our gallery. There's not that many objects for me to put up here for you, so I've just chosen 4 of my personal favorites. I'm going to focus on these 2 now, 2MASS-1207, the B object, which is the planet, and then in the HR8799, so I usually call this the Brad Pitt of planetary systems. If you have a camera, you photograph this thing. And if you have a camera that can photograph, everybody that could do a directly imaged planet, you do this system. Because it's 4 objects, they're all bright enough, easy to get. I shouldn't say easy to get. This was an extremely difficult measurement to make the first time it was made, and now we seem to be able to do it over and over again. So I'm going to talk about the B planet and 2MASS-1207b. Here's what the spectra look like for these objects. And without going into too much detail of all the things that are going on for this, estimated effective temperatures for this object for 2 mass 1207b is 1600 degrees Kelvin, and for HR8799b is 1100 degrees Kelvin. So both of these are square into brown dwarf territory. That's the effective temperature regime that I've been working on for years and years and years. It's just, well, I'm not that old, but you know what I mean. The objects are, the difference between those objects and the common objects that I study is that these objects are young. So what does the youth do to them? That if you were to just find this thing in isolation, you would find it weird for 2 major factors. One is that the H band, so I referred to the J band and the K band earlier, we call between 1.4 and almost 2 microns the H band. It's a triangular shape. It's not a bowl-y shape as we're used to seeing in regular objects. The objects have very red near-infrared colors. So in the case of, sorry, I actually have these reversed. 2 mass 1207b has the J minus K color 3.03. That is off the charts. We don't know anything isolated that's as red as this object.
So,
Yeah.
what are the units? I assume you call it J minus K, but I assume that's in some sort of logarithmic sense,
Yeah.
right? So that's probably a ratio. Which
Right.
band is J and which band is K?
J is the 1 to 1.4 micron band, and K is the 2 to 2.5 micron band. So that's telling you how much flux is actually shifting into the red. So it's a positive number, so that much of the flux is in the red, so it's a K band. If it were,
Then why isn't it K minus J? I'm kidding. I don't want to get
magnitudes.
yeah, it's just the magnitude difference between them. But the important thing to know is that these objects they're red, and they've got this triangular shaped H band. So it took a lot of work to get to the point where we were like, these things are weird. They're very red, and they're triangular shaped. And this went on its own. Outside of the brown dwarf community, we didn't really communicate that much. And at the same time, there was work being done on the brown dwarfs where we were just going around and finding them, and out pops this population, which is the population that I've been studying. Yeah.
Do you know J minus K for Jupiter?
I don't know. Somebody's asked me that before, and I don't know what it is, and I think that it's confusing because that's in reflected light. So it's not going to be quite the same thing.
Right, I should get a sense for what when you say J minus K.
Yeah.
Is weird, but I don't know what does that mean weird?
Well, I'll put it in context with brown dwarfs. It's weird in context with brown dwarfs. And by the end of the talk, you'll see what cold objects like Jupiter look like in near-infrared minus mid-infrared colors. Jupiter's weird because it's reflected light, and these objects are isolated. So this is their own flux. You're looking at they're radiating out because they have gravitational contraction still. They're still trying to contract, they're not able to because of electron deformation.
Do I understand that you're saying that the radiation is not black body radiation because that triangle?
Yeah, well, so that's, so the triangle is shaped because of various absorbing features in the atmosphere, and largely because of collision-induced H2 absorption, which is happening in the K band. And so you can have more or less collisionally induced H2 absorption, and that will sculpt the slope of H band. In between H and K band is a telluric region where the Earth's atmosphere is actually absorbing a lot of flux out too. So the Earth's atmosphere causes a lot of problems for us in terms of understanding the spectra. But here's my gallery. This is the gallery. These are the objects that I call analogs to young giant exoplanets. And honestly, some of these objects aren't just analogs. Some of these objects, which you'll see in about 10 minutes, these objects, I've given them ages. I know that their masses, I know that they're in the same moving groups, same associations as some of the exoplanets. They're equivalents, but they're isolated. They're on their own. They don't have a parent star. They're orphans. There's lots of words we use for them. I love this. I love this collection of objects. I want to go into their features. So we've been studying these things. A lot of them were serendipitous, where they were discovered. We compared them to equivalent objects, and they just look weird. So for instance, I'm going to focus on the objects that we call L-type objects. So these are objects that are between 1,000 and 3,000 degrees Kelvin. Here's your J band, your H band, your K band. I've demarcated various important features in their spectra here. So these objects they have crazy atmospheric chemistry. You've got iron hydrides, you've got metal oxide absorption features, vanadium oxide, potassium alkali lines in their spectra. There's the collision-induced H2 absorption, carbon monoxide, and I'll talk about the clouds in these objects in a few slides. But this is what normal objects look like. These are average templates, too, that my colleague Kelly Cruz has been working on. So this is what a normal object would look like. And then out pops these objects that, maybe you don't look at them and see how weird they are, but I look at these and think, what the heck's going on? How can these be the same type of object? You see this same H-band issue. This is at the lowest temperature in the L dwarfs, for which I'm showing you here. You can see another sharply peaked H-band. Anything in red is what I've decided. I culled out of all of the spectra that I had of brown dwarfs, and I said, that looks weird. I don't know what to make of that. There's also this feature, the iron hydride or the vanadium oxide. This slide is, I don't know why I can't see it. Okay. The vanadium oxide, you can see that the shape of the vanadium oxide is different. The younger objects have much deeper absorption. This is a weird effect that took us a really long time to figure out what was going on, but it's a temperature effect. These objects are not the same temperature, so it's not a really good idea to put them on top of each other, but they're mocking the same temperature because of gravity issues. We couldn't figure that out until we knew their ages. Potassium lines are different. That one we had figured out pretty quickly because this is something that is a gravity-related issue where you get less pressure broadening, so you get potassium lines that are either weaker or narrower. And so that was one of the first clear indications that these objects were young. We didn't know how young because you have no way of really telling. That's the catch-22 here. Like, these things look young. How young? How are you supposed to be able to tell? They are also red. So this is what the normal spread in the near-infrared color looks like. So here's the near-infrared color on the x-axis, or the y-axis, spectral type here. So you can see there's tremendous spread here. And this is just my collection of normal objects. And so, you get a lot of scatter in here. As the objects get cooler, they're actually getting redder. That's in large part because of more mineral species that are able to condense out in the atmosphere, so you get these crazy clouds. Yeah.
Sorry, I'm not clear. What makes you decide that these are the normal ones and that the other ones aren't the normal ones?
So there's a couple reasons for that. These objects kinematically are consistent with a age of thinnest stars. This is also the bulk of the population. Those other objects are just a handful. So I don't know why. I mean, it was object upon object that looked the same until these other objects, which were all red. And so those same objects that showed those weird spectral features, they're also popping up into the red. They're all redward of where you would have expected them to be. So that's why we say, they're red and weird. This suspected young L dwarfs, I keep saying suspected. The spoiler alert is that I know some of the ages of these objects. They're up to almost a magnitude better than J minus K. This is one of my favorite objects that I published a study on in 2013, Mass 0355. That object is crazy red. It rivaled the planets, and I was convinced it was a planet when we first started looking at it. And then as I studied it a little bit more, I figured out that it was a bit older than I was suspecting. That redness continues into the mid-infrared. So that was an important observation to make because the flux is shifting into the mid-infrared. They're red from J minus K, they're red from W1 minus W2, or 3.5 minus 4.5 microns. The flux is shifting into the mid-infrared. What would make something shift flux into the mid-infrared? The answer is clouds. So the big conclusion that I'll be getting to through the next 3 slides is that these objects that are younger require thicker clouds in order to explain their near-infrared colors and also their luminosities. And that is a harmonious explanation for what the planetary scientists also, or the people that are studying planets, came up with. This is another very important diagnostic tool for looking at the features of these objects. This is a color magnitude diagram. So I've got the near infrared color again, such an important lever for us in understanding the physics of what's going on in these objects. Most of the flux is coming out in here, which is why we use this as a lever. Versus the absolute magnitude. So I've measured parallaxes for a lot of objects. This diagram is populated with a lot of my parallaxes, supplemented with a lot of parallaxes that were done by other teams, which I'm noting here. But everything that's going on in this figure is telling you something about the physics of what's going on in these objects. So for the L-type objects, I've color-coded the L-types for early, the red and blue. At these effective temperatures, condensate dust clouds are actually really important. These objects have mineral clouds in their photospheres. And I'll go through a little figure on that in a minute. By the time you get to the T-dwarfs, though, the dust clouds disappear. They're settling below the photosphere so that you don't actually see them, and methane is really all you're getting out in your direct data. In between, you get this crazy thing happening at the LT transition when you're moving between these two types where the clouds start to clear. But so the models will look at this, and the modelers said, okay, I think we can reproduce this if we have this sedimentation parameter where we can move around the cloud and the mineral species that's available in the photospheres of these objects. And then you can tweak metallicity and you tweak gravity so that you can go through the values that you think you should be able to get physically. And each one of these lines is basically, I took synthetic spectra that's produced by various atmospheric models, integrated it out to get what their flux would be, and that comes up with these tracks. And so everything in between the leftmost and the rightmost line shows that the models could tell you how you got to those magnitudes and those colors. And so while the elbow never quite reaches the extent that the LT transition, the objects going from an L dwarf into a T dwarf out to, was pretty good. So anything that spills out of these lines is telling you you have a weird object. So here are the planets. The planets became a massive problem immediately because they're at the effective temperatures of, I've color-coded them to what effective temperatures they should be, but they were not what we expected. They were redward, which I already had mentioned. They had crazy red colors, and they were under where you would expect them to be. What we were initially calling underluminous. So the modelers went and said, okay, I think we can figure this out. The problem is that what we have not taken into account for is that these objects might have very cloudy, very thick cloud decks in them. So they went and extended their tracks to produce these enhanced cloudy tracks for us, all for the planet. For the planet, the directly imaged planet objects, basically for HR8799b and 2mass1207b, and that fits them pretty well. So then when I checked with my objects, they fit pretty well too. So the conclusion here, so every one of the objects now that's overlaid with a black circle is an object where I have myself or another team has measured a parallax for an object, and we find that they are redward and under where you expect them as well, fitting along the enhanced cloudy tracks. So more into this conclusion that these objects have enhanced clouds. So what are these enhanced clouds? Here's a little schematic of Jupiter clouds. So this is Jupiter. This is as you look down into deeper, hotter, denser layers. So it's fascinating to think about the cloud species that are in Jupiter. At the primary layer that we see is ammonia clouds, and water clouds. Trapped below that is some methane gas. Now, as you go down into, as you go up in temperature, closer into what the brown dwarf territory is, you strip away these upper layers and you start to probe into a deeper layer of something like Jupiter. So here's what the cloud layers look like on something like a T dwarf, which is about 500 degrees Kelvin. So methane gas is what's dominating. The potassium chloride clouds, there's sulfide clouds that are trapped below those layers, so you actually don't see them, which is why we regularly call T dwarfs to be pretty much cloudless as far as our perception of their spectra go. And then the L dwarfs, which are the objects that I'm mostly talking about. And these are crazy clouds. mostly there's noxious gas in the upper photosphere, so it's carbon monoxide gas that's dominating. But then you have these magnesium silicate clouds. There's liquid iron metal clouds. So iron hydride has formed in these objects at the cool temperatures. And then as it cools, the iron actually goes to liquid form, and you get liquid rain of iron in these objects. And then at the deeper layers, you get this perovskite and corundum. So I guess you guys would know this best, the corundum in a crystalline form. You get sapphires and rubies. That'd be awesome. Rain and money on these objects. It would depend on the impurities and whatnot. And they have to be in a crystalline form. It's not, anyway. It's fun to think of the exotic nature of the photospheres. But regardless, this is the common picture of it. The objects that I just said, they're enhanced clouds. So these objects actually have enhanced, thicker clouds. So on to the ages. So,
Wait, Jackie,
yeah.
why do you see such prominent features from things like vanadium oxide and potassium iodide then, and not these more abundant phases?
Because they're trapped below, so a lot of, I didn't actually mark where the visible layer is, where you can actually see down into. So carbon monoxide is a prominent feature in there, and you can't actually probe down into seeing the perovskite or the corundum.
Okay, but I'm still curious, like vanadium's not a very abundant element. There's going to be other refractory oxide molecules we think would be more abundant. Or are these stars enhanced in vanadium? I'm trying to understand.
Oh, I don't think that there's ever been suggested that they'd be enhanced in vanadium, but it's a good question. I don't know. It is one of the more abundant species that's present, though. I had never thought
An
about
accident
it.
in molecular spectroscopy that is just
Yeah,
has a stronger signal.
it could be. I don't know. I don't know what this. Yeah, I'm not sure.
Have you found sodium chloride?
No.
No.
We have sodium.
Just potassium. Well,
Yeah.
sulfide, yeah.
Yeah, so we do have sodium, the sodium lines, sodium 1 lines. Okay, so on to the question of their ages. This is a little movie that I've rendered for you. Just imagine yourself, find a dark sky, sit there, open your eyes, leave them open like a shutter, and keep them open for roughly 1 million years. You'd see this. All of the stars in the nearby neighborhood, they're moving. All of the stars are moving, actually. But the ones that are close by, we can detect their motion. And so we just sort of move time forward so that you can see how some of these objects are zipping forward. I want to call your attention to this feature here. It's not a feature, it's an asterism. That's the Big Dipper, the famous Big Dipper. And the Big Dipper is actually a collection of stars that's co-moving. Those objects are moving together. And so see the asterism stays together. Nice. Not all of them are actually moving together, just 5 of them, I think. That is something called a moving group. So in the vicinity of the sun, this is another little movie I rendered. Actually, Adric Reidel, our postdoc in our group, rendered. This is a little viewpoint of the nearby solar neighborhood. Ursa Major is now marked on here. Every little dot on here is a star, color-coded when we have done an insane amount of kinematic work to decipher that these objects are moving together. And they're mostly higher mass stars. And the higher mass stars, we have a lot of tools at our disposal for determining their ages. And so these groups have pretty well-defined ages. This is out to about 100 parsecs from the sun, and a parsec is about times 3 to get to light years, so 300 light years away from the sun. You find these groups. They're sparse, they're not concentrated on the sky, so it's not like the Pleiades or even Ursa Major, which is really nice and compact. At least you can see the general vicinity of it. It's not like that. These objects, these groups, are actually harder to tease out where they are and how you find them. But they are the hunting ground. These groups, they are the hunting ground for exoplanets because they're younger. They're between 10 and 150 million years old. And 10 and 150 million years, your planets, if you can find them, are all going to be brighter and easier to study, which is why we go after them. So, Beta Pictoris, B, this tiny little dot in here, which is the actual planet, that's in the Beta Pictoris moving group. AB Pic, B, which is that object, is in Tucana Horologium. 2 mass 12 with 7b is in TW Hydra. And HR 8799 is debatable, but it's in Columba. So, where are my objects? I've gone out and measured parallaxes, proper motions, radial velocities. It took several years. We put the kinematic picture together, and we found the following. We've got a comparative sample, 13 objects that I would definitively place in Beta Pictoris, which is about 20 million years old, 16 objects in Tupano-Horologium, which is 30 million years old, 8 objects in Columba, TW Hydra, 5. This has its own implications. This is awesome. We've got ages. We can nail down exactly what's going on with all these objects. You can get masses. But most importantly, they're in the same moving groups as the planets. So the great, beautiful thing is that they can be studied in situ. You can look at them together, and they're at similar temperatures. It should make you raise the question, they're at similar temperatures, they're at the same age, aren't they the same mass? And so that's also part of the new question. This is back to that original figure I showed, the age versus now the luminosity. I've overplotted the black dots are my full sample. The purple dots are where the planets are. And you can see I've got a comparative sample in Beta Pictoris. I actually didn't show the TW Hydra objects on here. Between 10 and 20 million years old, 30 million years old, 150 million years old. There's a few objects in here that you can see are less luminous, probably less massive than the planets, the objects that we're calling planets in these groups. So they're a fantastic sample for comparative studies. And the last thing I'll say on these objects, before I'll go into focus 2, which is the colder objects, is that this is the sequence of objects that I have in Beta Pictoris. So this is their spectra. This is the spectral evolution from 1400 degrees Kelvin to 1900 degrees Kelvin of objects. And smack in the middle of these is the Beta Pictoris B planet. Sorry, I'm not clicking very well. So the point would be that you have this whole spectral, I have a whole spectral suite of things for you to look at and compare to your favorite exoplanet.
What about the Hyades?
The Hyades is annoying because it's 500 million years old. And so these spectral features and the interesting things that I've been noting don't seem to continue on at 500 million years. It really seems like 150 million years or so is where things start to settle down. Okay, now, so that's, I'm going to end on the young brown dwarfs there. I'll return to them at the very end of the talk, and I'm going to spend just a few minutes on the other thing that I've been doing. Focus number 2, the cold brown dwarfs. This is where things get so crazy and amazing because of a discovery that came out this week. So, you can go after the young brown dwarfs, which has been my primary goal, because they're easier, because they are brighter, because they are hotter, and they're in the same movie groups, they've got lots of exciting bits to them, or you can go after the cold brown dwarf. Now, this has been an active, very competitive area, but it's really hard to get to these objects because they're cold. So now we're at a similar problem as with the directly imaged exoplanets are having, where you need big glass, you need large telescopes, you need a lot of time in order to study these objects. But regardless, we've made some amazing progress at detecting objects that creep lower and lower and lower in temperature. Essentially, the tail end of what stars can form. And here is the gallery, another gallery of objects. This is the Y dwarf gallery. So these, I was referring to the L dwarfs and the T dwarfs, and a whole new spectral classification came on the market in 2013 when objects were discovered below 300 degrees Kelvin, below 400 degrees Kelvin. These objects are knocking on the door of Jupiter, which is at 125 degrees Kelvin, and they're likely at a similar age to Jupiter. So these are likely just your generic thin disk age of 1 to 5 billion years. This is the collection. You can see that most of these, actually all of these, were found through the WISE survey, the Wide Infrared Survey Explorer. Not all of these were easy detections. this was an object that we worked on, myself and Chris Tinney, where the object, which is this thing here, was sitting on top of a very bright, relatively bright 2-mass star. So we had to get rid of the 2-mass star before we could study that object. Similarly, 2056 is this object in here, which is also sitting near a very bright star. And now I want to tell you about this object, 0855. This object, the paper came out just this week. This is our newest neighbor, a pretty much phenomenal discovery that was made by one person, Kevin Leman, in a single author paper, where he went through the entire WISE catalog, searching for objects that moved between WISE to WISE images, because the way the WISE survey ended up imaging the sky is that it did this interesting loop elliptical orbit, imaging objects and turning as it did so. And so there was a difference between some of the images. So you had a baseline between images where you had some time that went on between them. And then in the end, the full catalog is just combining all of the images. But if you want to, you can go back and through all of the detections of these objects, which is what he did. And in doing so, he found an object that was moving, that looked like it was moving at roughly 5 arcseconds per year, which was a massive motion. It was unclear what it was at first. It's clear now what it is. This is the 4.5 micron detection. So he had to actually go and get director's discretionary time in order to get the real detection. And I'm going to blink this for you. So this is 4.5 microns. This is the location that it was in the WISE images. And I'm going to show that in a second, why this was such a crazy discovery. This is the Spitzer imaging. He got 2 epochs. They were separated by 6 months, and he saw this. If I saw that, I would have peed my pants. That is amazing. Are you freaking kidding me? This object moves at 8 arcseconds a year. It would clear the face of the full moon in 200 years. In our lifetime, you would see it walk across half the face of the moon. That is unbelievable. And it's at 2 parsecs. It's the 4th closest system. We didn't know about it. It was hidden. Now, who knows how many other objects are like this? It was hidden. So, I knew that this object was a potential because he had randomly thrown the coordinates into another paper. And so I saw the coordinates and was salivating, like, oh my God, Kevin never makes a mistake. I don't know why he put the coordinates in here. So I've been doing my own imaging of it. So here's my image of the field that it was in. And this is annoying, right? Because this is the field that the object was in. There's this contaminant. It was sitting on top of a star. It was sitting on top of another star at the time that the WISE images were taken, so that the WISE color was off, which is why the WISE team was perplexed by this, because you could ask yourself, how did a single person find something like this when the entire WISE mission literally was developed to find these kinds of objects? And so I was going after this thing like crazy for the past few months, although failed, I guess. But Kevin deserves every ounce of credit for finding this object. There's a darn galaxy cluster in here, which is also annoying. But the problem was we didn't know where it was because you weren't sure about the proper motion, because it's got a major parallax and it's got to move. And so it was slightly confusing. What I'm calling a rogue planet, so this object, would have been here in my images based on Kevin's parallax and proper motion, but I didn't detect it. So this is going to be an important measurement to make, and I'm planning on spending 3 hours on this object when I go back to the telescope in May, because all we have is an upper limit for this object, but holy moly, this thing is cold and faint. Yeah.
So why is it not what you thought it was going to be?
Well,
You
it
said,
is.
You looked for it here and it wasn't.
It just wasn't detected. I didn't get it. So I didn't go deep enough on the image.
It's too faint.
It's too faint. All I can say is that I have an upper limit on how faint it could be.
So is that image you just showed us? That's the image where you were looking for it.
That's where I was looking. But I didn't know where to look, because he had found it here in WISE. He had given a proper motion, which was 4 arcseconds per year, which would have placed it in here somewhere. So at first I was like, oh man, maybe it's that. But no, because I had actually done some J3, J2, which is looking at two different parts of the J band, so that's actually sampling the flux for Y dwarf really well. But it doesn't move at 4.5 arc seconds per year. It moves at 8 arc seconds per year. So it's here. So I didn't, I mean, you know, it's just, it's a fishing expedition.
I see. So if it had moved with the proper motion that he reported, it would have been at that first.
Well, it would have been somewhere
just
in
beneath
here.
that little
Yeah.
blob there. But in fact, there's been a revised proper motion estimate.
Yeah.
You're saying that puts it at 8 arc
Right.
seconds per year. So
It's over here.
it should be over there in this image, but you don't see it.
Right, I don't detect it. And so I'll say that I actually reassessed the proper motion from his original imaging, and I got way closer to the original, to the number that he now reports. So I already had a feeling that it was moving much faster. But it didn't matter, I didn't go deep enough. Anyway, we'll go deep enough in a month, and we're gonna fill this in, because take a look at this. This is crazy. This is with the spectral types. This is how effective temperature changes, and this is how the flux changes. Now this is J minus W2, and you can see, whatever, L dwarfs, I was so excited about them earlier, but blah, blah, blah. Then, man, they drop like a rock. All of the flux is shifting. All of the flux is moving into the mid-infrared. So we've been working on this, myself and Chris Tinney. I've been trying to get parallaxes for 17 of these objects that are what we call the coolest ground-based parallax program around. And we find the following. So the absolute magnitude in W2 versus and J-band. The L dwarfs, again, they're pretty monotonic as they decrease. I could go off on a tangent on how they're not actually that monotonic when we start including the young objects on here. But the LT transition is just unbelievably weird because you get cloud clearing in there. But as you get to the lower temperatures, you start to see these things that they drop like a rock, especially when you compare them to what's happening at the earlier objects. And so 0855, oh my goodness, what's happening there? This object is so faint. And I'll say this was a paper that came out last year by Trent Dupree and Adam Krause, two friends and colleagues of mine, which was a competitive program to our own, which we haven't had a chance to publish our wide dwarf parallaxes yet. But what they found was, they're like, hey, look at all these luminosities for the wide dwarfs. It was a small sample, but they all looked like they were the same. They all looked like they were tight. They didn't look like they had a luminosity spread. It didn't look like you could find something like 0855 because you weren't going to drop like a rock. But we've found something quite different. So this is a paper that we're about to submit showing what the luminosity spread is for these objects. And so we find that there is a lot of luminosity. 0855 aside, we found diversity. And what does that diversity mean? Anytime you see diversity, it must mean something. This is a color magnitude diagram again. So for these wide dwarfs, the clouds are back. The clouds which disappear into the T-dwarfs, they're back at the wide dwarf temperatures. At least this is what we're proposing. This is the near infrared to mid infrared color, the J minus W2, versus the absolute magnitude in the Y's W2 band. And what I've overplotted here for you would be a cloud-free model. These are all from Caroline Morley, who's a grad student at the University of Santa Cruz. We call her the Cloud Ninja because she is one of the only ones that's producing models for us at these effective temperatures that take into account the correct refractory elements. Sulfide and water clouds, similar to what's in Jupiter, need to be taken into account here. And so the diversity that we're seeing in the luminosity of these coldest objects is likely due to the clouds. What 0855 is going to mean, I'm not sure. I will say that I've plotted the W2 magnitude here, but I think that W2 is contaminated because of that weird source. I'm not sure how contaminated it is, but it's certainly contaminated. Okay, so the summary from these two focuses is that enhanced clouds are correlated with youth in brown dwarfs and planets. That's what's coming out as a whopping result from the young object analysis. And in the coldest brown dwarf, the clouds are back. They're not the mineral species clouds that we were seeing in the L dwarfs. Now they're sulfide clouds, or water clouds, which are redistributing the flux in an interesting way. And so I'll end with this comment about the masses. This is our perception of how these objects form. Brown dwarfs form through the collapse of a cloud. Planets form in a disk around a star. Is this the right picture? Did some of these objects that I just referred to form this scenario or this scenario? question, an awesome question that we're trying to go after. I don't know if we'll ever be able to tell. Microlensing results certainly came up with this interesting result in 2011, claiming that there is this population of unbound Jupiters that are up to twice as common as stars. This was a controversial result. It was in Nature. I don't know what that could mean. And they claimed that there might be this planet-induced mass function turnover at 5 Jupiter masses. Perhaps these objects are along those lines. So I'll conclude with these 4 thoughts. This population of objects is amazing. They're isolated. There are only a few Jupiter masses. We're using them as analogs to exoplanets, but in many cases they're equivalents. And they are the best sources to help characterize future exoplanet discoveries. From the luminosity sequences that we've developed, from the spectral features, the spectral library that we're offering out to the exoplanet community, to the near-infrared photometry that we have, so our ability to analyze what's going on with these objects, to then inform the models what we think is going on. I think this population is well suited to really helping future missions. Okay, I'll stop there.
Back up your slide by 1. That's it.
Okay, Wayne, looks like you're ready for the first question.
What's Gaia going to do for you?
Oh man, I love Gaia. Mostly because I was on the SOC for a Gaia meeting last 3 weeks ago. Gaia doesn't do a ton for brown dwarfs. In total, I can give you the exact number. It's going to cover about 600 brown dwarfs in total. It's going to get 2 T dwarfs in all of total. This object called Lumen 16b and Epsilon Indy B. That's it. But what it could potentially do is redefine these moving groups that I was talking about. Because we need to know how those objects move in order to say whether or not there are more objects in them. Oh, Gaia's going to do everything though, because it's gonna redefine all of the moving groups in the nearby vicinity of the sun. So I just showed a couple. So none of these things were obvious until Hipparcos
Like it
showed
did
up.
for the Hyades.
Yeah.
For the Hyades.
Yep.
Right.
It's going to be amazing. Gaia's going to be amazing.
Carl.
You mentioned that there's spectral broadening of some lines due to gravity. Why can't you use that to constrain the masses?
So because we don't, it's a very broad general result, and it's not one-to-one. There is something we're doing with spectral indices, so trying to use this new sample in order to calibrate against the known sample. There's one glitch to all of this in that there are some objects that just look dusty, and dusty objects mock some of the gravity features. So it appears that gravity and dust clouds can do the same thing. So it's not as clear. I made it look much prettier than it's turning out, than it is.
Let me ask you a question. Do you happen to know why Kevin was able to find this wonderful object and the WISE team was unable to do it? Did he come up with some clever way of using a computer to effectively blink the plates at the different epochs that the WISE team didn't do? I mean, what's the details of how he managed to
The
pull
WISE
that?
team knew about it. I was working with the WISE team on it. It had been found. It was considered. They thought it was a contaminant.
Oh.
They didn't know, and Kevin didn't think it was a contaminant, and he really pursued it.
Right, so he knew where to look. He knew which one to focus on. It's
Well-
not like he did 10,000 plates to find this thing.
No, he did.
Oh.
Yeah,
I see.
he sat there and blinked image after image after image. I can only imagine for 2 years
By eye.
by eye.
Okay, this guy deserves a medal of a different sort.
He really does.
A masochist medal.
You have to look at each image in order to, because there are artifacts in these catalogs. There's diffraction spikes from stars. There's contaminants. There's all sorts of things where you need to visually inspect. But it's not. Lumen's awesome. He also came out with a discovery last year. It's called Lumen 16. It's also groundbreaking in terms of it's at the LT transition, and so the objects are very cloudy. That object is also at 2 parsecs. He found it in the same way as he did this one.
Yeah, were you a co-author on that paper?
No. I have a Lumen 16. I have what I'm calling the Lumen 16 paper that's about to come out, but he's not on the paper.
Old-time
just asked-
astronomy still has its uses.
Oh yeah.
Well, I just asked because I actually observed Lumen 16 a couple nights ago. We have 3 epochs on it, so we now have a parallax. I can tell you what the parallax is.
We should talk about that after.
Yeah, we should talk afterwards. Larry?
You keep saying this, can you explain what you mean by contaminant? Is that like a dust particle on the telescope?
So a contaminant means that there was a star that was sitting on the position where it was at the time that the WISE imaging was done. That is, you know, whatever. It could be at 150, it could be at 500 light years away.
But I thought he found it in WISE images.
He did, because it moved between one epoch and the next, but this star is still sitting there, contributing some of the flux to it. So that's also part of why it's so amazing.
So during one of those epochs, it was sitting under another star, is what you mean by contaminant?
Yeah, right.
Sorry.
Yeah, so that,
Over another star,
right.
hopefully. The star's far away.
But so we know, this happens all the time. It does happen.
Sure.
And it's part of why you probably have objects like this that are hiding. There's lots of stuff that's hiding behind the stars. Yeah.
Actually, I should say that Sandy Kaiser knows the parallax to this sphere. She's the one that did the data analysis of the three epochs. So we should bring Sandy into that
Nice.
post-talk conference as well. Any other questions? Back. TJ.
If this new object is red,
Louder?
what's that?
Louder?
Oh, if the new object is red, why not go for it at K-band?
Oh, there's no flux whatsoever coming out. Okay, yes. So the J minus K color for Y dwarfs is actually blue. So most of their flux is coming in J band. But also the sky is very bright in K band. Our atmosphere is very bright. So K band is really hard to go after. You want to be able to integrate for a long time so that you're not sitting there with 10-second integrations over and over. At J band, we can take I take 60-second integrations before the sky gets to the point where it's unreasonable. Yeah, there's not a lot of K band imaging done for the Y dwarfs, though I have some that I've done.
Any other questions? If not, let's thank Jackie again.